I'm super excited to be here today at CppCon. It's the first time for me to be at CppCon, but I think we actually have some interesting things to talk about. And what I want to talk today about is lessons we learned from a decade of dealing with the issues of performance portability in scientific computing. I myself am from Sandia National Laboratories. So for those of you who don't know about Sandia, we are actually the largest of the US national laboratories. We are located mostly in Albuquerque, New Mexico, and we are one of the nuclear weapons labs in the US. So we are dealing a lot with that kind of security, non-proliferation and stuff. But we also have a lot of general scientific things going on, including research into renewable energies and cybersecurity and all kinds of other things. And a significant fraction of the 15,000 people who work at Sandia are involved in computing, doing simulations and things like that. There's multiple thousand people with PhD doing just scientific computing at the lab. So what do I want to achieve in this talk, right? I want to demonstrate some of the issues heterogeneous hardware has in terms of performance portability from a C++ software design perspective. I will try to show you in examples using Kokkos, which is the project I'm leading, how we can address some of these concerns. And then try and connect that back to C++23, MD-SPAN, and maybe a bit about StudBLAS, and how these things we learned over the last decade in developing stuff like Kokkos flow into these features in the C++ standard. What I'm not going to try and do in this talk is I'm not going to try and give you an actual introduction into Kokkos, because I don't have time for that. I'm not going to cover lessons really regarding asynchronicity and task systems. I think the next speaker will talk a bit about that. That's just doesn't fit in here time-wise. And I'll also will not spend much time on trying to explain how GPUs and these kind of accelerators actually work, right? That's gonna be a bit too excessive, always. Okay, so the outline, I'm going to talk a bit about HPC hardware and software landscape. Why do we have that problem of performance portability, in particular in scientific computing? I'll talk then about a number of these portability challenges before then connecting it to the C++ standard features we've been working on over the last decade as well. So why do we need performance portability? There's this list, the top 500 supercomputing systems in the world, which gets updated every 6 months. And basically what it ranks is there's this benchmark, HBL, which essentially does matrix multiplications in the end. And that benchmark has been around for a long time, for decades and decades. And you run that on that big supercomputer and basically you try to figure out how fast can you do this kind of calculation, including communication over the network, right? And it's a really important thing for us, right? Congress is interested that, the US is really high on that list and has a lot of big machines in that list, right? And that's one purpose of the national labs. And as Damien said, Oak Ridge is one place where that happens, right? And which had top 1 machines. All of their last 4 machines were top 1 machines in that ranking. And if you go back to 2007, right, and you looked at the top 10 machines, right, it turns out they ran 3 different architectures. They ran Intel Xeon processors, they ran AMD Opterons, and they ran IBM Power. Right? And each of these had either 2 or 4 cores per chip, right? And that's it. And we were programming that thing, and we were running MPI on it, a message passing interface to communicate across these things with low latencies and stuff. But that's basically it. If you look at the last top 10 machine, right? Instead of 3 architectures, which differ in 2 or 4 cores, you now have 5 different kind of CPU, host sockets, combined with 4 different accelerators in various combinations, right? So we have, all the normal CPUs, Xeons, AMD, EPYC processors, Power 9s, Fujitsu, etc. But we also have NVIDIA GPUs, AMD GPUs, and then the Chinese have actually 2 of their own accelerators as well. And if you then look how you want to program that thing, right? On the CPUs, we now have to use some kind of threading model because we have so many cores per socket that running a process per core just doesn't work, right? Essentially, you would split your data in so little chunks that you have a surface to volume ratio. Everything you have is kind of borders, and you need to communicate all the time. So instead of that, we needed to introduce, threading, and we did that with OpenMP, maybe threading building blocks and stud threads, right? That's the three models which are supported by the vendors who sell us these machines. But when you go to the accelerators and the models the vendors give us, right, and want us to use is NVIDIA CUDA, AMD ROCm, Intel's OneAPI, which is based on SYCL, OpenMP offload, which is actually different than the OpenMP we used for CPUs, and maybe OpenACC. One thing you will notice is not on there, right? There's no OpenCL really on there. There's no OpenGL on there. There's no Vulkan on there. There's no Metal on there, right? This is the models we get given. And most of these are C++ based, right? So CUDA, ROCm, OneAPI is all stuff we can only use from C++ compilers, right? OpenMP and OpenACC also work from Fortran or C. And the problem is, what you see here is that the hardware architectures and the means to program them have diversified, right? These models also are not available on every platform, right? OneAPI is only available on the things, which will come with Intel GPUs. The AMD ROCm thing, right, is not available on our CUDA platforms necessarily, at least not vendor supported, right? You can kind of make it work, but it's not something you can say, oh, I have a bug here, please fix that vendor, right? We say, this is not supported. NVIDIA CUDA, right, is not supported on any of these other platforms. And that's our problem, right? But we have all these different models we need to use. Kokkos is our solution for that. Essentially, everybody writes to Kokkos, right? And then Kokkos maps to these underlying things. So what is Kokkos? It's a C++ programming model for performance portability. And we implemented it essentially as a template library on top of CUDA, OpenMP, HBX, right? This is the kind of zero overhead principle, right? Everything gets essentially compiled directly into the native model underneath. One of the real big goals we have is we want to be descriptive and not prescriptive. So what we've done is we actually came up with all our own semantics. As our programming model has its own semantics, which then just gets mapped on the semantics of the underlying programming model, right? We are also trying to align with the development in the C++ standard, right? So some of the features we are doing is stuff we are trying to get into the standard. And that's where MDSpan, for example, is coming from, as I will show later. And it replaces usage of things like CUDA and OpenMP in our codes, right? We don't use these raw models anymore in our applications. We only use it inside of Kokkos to implement the abstraction. There's more than the programming model. There's also other things we need in scientific engineering computing. There's math libraries, there's tools, etc. It's kind of like in the CUDA ecosystem or OneAPI ecosystem, right? Where you don't just get a compiler, you also get all these other things you need to, be productive. It's open source. The whole thing is under permissive license. It's available on GitHub. That's where all our maintenance and development happens. So while we are, a US national lab and we also deal with, secret stuff, this thing is completely developed in the open and usable by anybody in the world. The Kokkos ecosystem is, kind of what I said about, there's all these different pieces we need in order to make users really productive. Kokkos Core is the programming model. So mostly I'm going to talk a bit about, that thing as related to performance portability. But there's Kokkos kernels, which is like linear algebra, graph kernels and stuff. There's support, which develops just like tutorials, documentation and whatnot. We have funding for that. There's tools, which hooks into all of this to make it, profilable and debuggable, despite the fact that everything is hidden under, 5 layers of template abstraction. And then there's a couple of other things. There's interop. We have a project going on where we can essentially hook it up all in Python, and you can actually write your parallel algorithms in Python, and it gets translated into Kokkos. There's interop with Fortran. We're looking into things like remote spaces, which is essentially global arrays, partitioned global address space abstractions. And we're also looking into resilience. So we have projects going on where you could deploy that, and you would, for example, do redundant execution to deal in environments where you really need to make sure that you got the right answer. The Kokkos team is split across 5 national labs. So it's Sandia, Oak Ridge, Argonne, Los Alamos, and Berkeley lab, which are the main contributors right now. And we are all together kind of maintaining and developing this. Usage has been growing. So for scientific computing, we're actually pretty far along now. We have over 900 people, developers who are inside our Slack channel asking us questions all the time. At Sandia, it's the primary programming model we're using, so for our nuclear weapons codes, for our science codes and stuff like that. And at the DOE exascale computing project Damien mentioned earlier, which is this project from the US government to develop exascale computing software in support of the platforms we are buying. And that's actually to the tune of multiple $100 million a year, right, in funding, which goes into this big project. And a bit more than 50% of the C++ codes in there use Kokkos as their programming model. Only less than 10% use the native vendor model in any way. And mostly that includes things like Kokkos, which are themselves abstractions, maybe a bit more domain-specific abstractions than Kokkos, but practically none of the applications write in the native models, right? None of the applications write directly SYCL or CUDA or ROCm, really, right? We all use these abstractions at this point, more or less. And we have about 150 to 250 HPC projects which sit on top of Kokkos at this point. Okay, let's look a bit at challenges. And I'm gonna start, with fairly simple things, right? So if you did any of these kind of GPU programmings, a lot of these things might be obvious to you, right? But for other people, it might be a bit of a surprise. So this is simple CUDA code, right? There's a bit funky stuff going on. There's this global modifier there, which isn't proper C++. Basically what that says is this is a function you can launch from the host, but it's gonna run on the GPU. There is this little tribal chevron thing there at the bottom, which essentially says, launch this function, and here's the launch configuration. In this case, I'm saying I want one CUDA block with one thread, right? So I'm essentially just launching a single thread, which you usually would never do because you woefully underutilize any resources on the GPU, right? But keep with me for a second. And then the structure there is normal, like a data structure you might have, right? If you try to compile that, you get an error. And it basically says, you can't call this foo operator thing there, right? You can't call the bracket operator. And the reason that you can't call it, that it's undefined in device code. Where's that coming from? Essentially, we need device compilation markup. In CUDA, you have these host device things, right, as well as this global thing. And what that says, right, is compile this function for both host and device, right? Now, it's a bit annoying, right, but okay, you just do it. But where does it come from? The fundamental problem here is if you're not just compiling for a single architecture, right, for a single CPU, you actually have different ISAs, right? You can't just execute the code you compiled for the CPU, the bit code you compiled there on the GPU, right? It's a different instruction set. So you need to deal with that. You could think, I'm just compiling everything twice, right? Every single function, I'm compiling it for both sides. But there's a couple problems with that. One thing is GPUs can't handle everything. For example, you can't just randomly allocate memory, right? It's actually kind of problematic. You can do it in a certain limited way, but you essentially have to preset how much memory do you make available for dynamic allocation, which is a problem. Inline assembly or intrinsics for CPU architectures, right? That won't compile, right? You can't just call like SIMD intrinsics in code and then try to compile it for both sides, right? System calls are largely not possible from within device code, right? The functions will not be available. And often you can't protect this thing with things like ifdef avx, right? Because it turns out that these macros are defined in both compilation phases, right? Because we're coming at the preprocessor step, long before it tries to compile either side. You could probably fix that, and there's other people who can talk better about that than me, with things like speculative compilation, right? You can just try and compile it and, see what happens, and if it errors out because of one of the typical errors, you could say, oh, I'm giving up on that compilation path. But that makes the debugging, if you made a mistake, right? So did it not just compile because you didn't want it to compile or because you made a mistake? How do you know, right? So that's complication. As a consequence of all of that, most of the C++ standard library will just not work, right? Stud pair will largely not work, right? There's ways around it, but basically it doesn't work. It doesn't have a markup, right? Stud array will not work. You know, all of these things you are used to will all not work portably. So the lesson learned here is for single source compilation for heterogeneous architectures, you require some form of host device function attributes, right? There's related expert lessons, essentially, you know, which comes then a bit later, a bit more complicated. Function pointers, right, are a bit problematic because every function, host device function actually has two function pointers with different values, right? One for the host and one for the device. And which function pointer you get when you get it, right, depends on where you execute the get me the function pointer. That makes virtual functions also fairly tricky. Dispatch to devices and the challenges of value semantics. There's another problem. So say you got that foo thing, right? The thing which had like an array of values in it. And you want to actually write to it on your kernel. So let me take an, you know, if you're a normal C++ land, what you do is you pass a reference to that thing in your function, right? Great. Now it compiles and it crashes at runtime. CUDA exception, warp illegal address. The exception was triggered at PC0xD038D0. Okay. If you really know what this means, right, it says, oh, I'm trying to access memory which isn't really accessible from the GPU. Great. Largely, basically what's going on is, you know, the GPU can't just access all memory in the system. In particular, it can't access stack variables on the threads, right? And if you don't have the right patches and the right maybe boot setup for your Linux system, right, then it also can't access memory allocated with malloc. Right? You need special allocators, and only that memory will be accessible on the GPU. Vice versa, some of the allocators produce memory which will not be accessible on the host. Right? But the biggest problem here is, you see, I can't capture by reference, which means that practically containers with value semantics, right, are no-go. And if you look at the C++ standard, right, most of the data structures, the basic fundamental data structures we have, are data structures which use value semantics. So, lesson learned, data structures we want to access on both sides need to have reference semantics. There's a bit of a problem there, for the experts then. Proper reference counting is actually kind of problematic. It's really difficult and costly to make that work, if you really want to make it work. In Kokkos, we solved that problem. We have reference counting, but we return the reference count off in the transition to the GPU execution. And we solve that problem by allocations will fence all outstanding work. Right? We'll just, if you deallocate something because the reference count goes to end, we wait for every outstanding work we dispatch to the GPU. Okay, the next thing. Par and seek. Essentially, we need to restrict significantly what guarantees we give to users in terms of what we are allowed to do. The main problem here is that strong forward progress guarantees is not really a given on many accelerator architectures. If you look, for example, at this code, right, a little deadlock code. I'm doing something with thread ID XX0. It's essentially just an identifier of a thread within, you know, the CUDA execution. And I want to wait there, right, until some other thread set an atomic counter. The atomic cast, there's a compare and exchange. This will deadlock on NVIDIA GPU's pre-Volta architecture. If you just switch it around, it will not deadlock. And the reason is that essentially you have something like vector lanes, you know, threads which are not completely independent. And it will execute the first branch first, and then if every thread who entered the first branch is done with that, it will start executing the second branch, right? So you would need to make sure in this case that you actually start the thing which sets the lock, you know, the value first. And some accelerators might not even have a concept of a thread. If you talk about data flow-like architectures, right, there is no concept of thread. You still have a concept of concurrency, you know, all kinds of instructions happening at the same time. but you do not have the concept of threads at all. Basically, that means the only viable execution policy for us in the standard is power and seek. Everything else tries to give us guarantees or gives guarantees to the users, which let the user write code which is not portable across all these architectures. At least not very safely. So parallel unsequenced loops are the fundamental building blocks for performance portable code. Now, there's task systems, and task systems can be really useful, where you build like dependencies and stuff like that. But because you have, and I come to that in a second, so much concurrency you need to expose on things like GPUs, right? You can't actually have a single task per kind of thread thing or whatever, right? So the successful task systems will still have parallel unsequenced loops inside a task, which may not go to the entire GPU or the entire architecture, right? But which go to like a subset of that. Okay, that comes to a basic Kokkos example. So what you see here is a matrix ad, and what you get is these Kokkos view data structures. They're called views because they have reference semantics. They are reference counted, they are multidimensional arrays, and I'm going to talk about these guys a bit later in more detail. And what you see there is, I'm getting three two-dimensional things. One of them is non-const, and two of them are const. And then what we're doing is we are dispatching parallel fors. It's kind of like the for each, right? It just implies that it's parallel. We do not have an execution policy in the sense of the standard here, because all of these will always require power and seek, right? I give it a number. How many iterations do I want to do? I give it a lambda. In this case, with Kokkos lambda, where it includes the lambda syntax and the markup, the function markup, when I execute that thing. Okay. So I said we have a problem with data accessibility, right? Not all data is everywhere accessible. How do we control where to execute, right? How do we control where code executes and where memory is allocated, and how these two things fit together, right? That's a fundamental problem in performance portability, right? If you can't access all memory from every place you can execute on. And that's execution spaces and memory spaces. So in Kokkos, these views actually have an optional template parameter which gets defaulted to something I'm going to talk later about, which denotes where this type got its memory from, right? So it's a type-safe thing, right? A static, reasonable, or you can statically reason about where this memory lives. What you now can do down there in that, fourth line from the bottom, you can ask that memory space, what is your preferred place to execute on, right? If I wanted the thing which can fastest execute on that thing, right? What type of execution resource do I need? You can ask it that, right? And then you can use that thing to dispatch your work, right? So the idea is that we have memory types, right? And these memory types know where they are accessible from and what is their preferred execution resource, right? And the other way around, you can actually ask the execution resource, what is your preferred memory space to operate on, right? So if somebody gives you an execution resource, you can ask it, where should I allocate my temporary memory in order to, work on this thing? So the lesson learned here is that execution and memory resources need to know about each other, because you need to be able to reason about it, and you really kind of need to reason about it at compile time. Because if you get a pointer, right, if you get a reference object, right, you want to know at compile time where to execute. You don't want to have an if statement and compile your code for both CPU and device just in order to then later figure out, which one you actually wanted to call. Because that increases binary size, compile time, and whatnot. There's a couple more concerns there. It's not just about accessibility. There's also things like, is this memory, for example, page migratable memory, right, which can move between different memory spaces? Is there things like shared memory, right, which is only, or kind of scratch memory, on-die scratch memory? And on top of it, types are not necessarily enough, right? You could have multiple GPUs in your thing, and then it's not guaranteed that the memory on one GPU is accessible by the memory on by the threads on the other GPU, right? So you might also need instances on top of that, right, of these things. Okay. The next big problem is what I call the curse of cached versus coalesced data access. So in scientific computing, right, we have a lot of like multidimensional indexing happening. And what people used to do, right, in CUDA and C and whatnot, right, they write their arrays and then they do index calculations explicitly in their access, right? And the two main common index things for 2D arrays is you do C layout or Fortran layout, right? Row major or column major. And that's what you see the index calculations up there, right? Now, the thing is, if you compile this code, right, and run that on a CPU and run it on a GPU with both of these layouts, right, and try the performance out, what you see is that the C layout on the GPU is kind of shitty, right? You give up like 4x or so in performance. It turns out if you go to Intel Xeon or even worse, Intel KNL or something like that, you give potentially up even more performance. What we've seen on Xeon Phi architectures was up to 20x performance if you do that wrong, right, the wrong way. Now, do you want these if-defs in your code? Probably not, right? The reason where this is coming from is that on GPUs, adjacent threads, they want coalesced access. They are kind of more like vector lanes on CPUs, right? They want to access the same cache line. If they all hit the same cache line, you have one memory instruction instead of 32 memory instructions or 64 on AMD, and everything is great, right? On CPUs, however, right, I parallelize just the outer loop. On CPUs, I have the problem that if I'm now going through that row, the same thread wants to hit the same cache line for the next element, right? So you want the row to be consecutive instead of a column you parallelized over, right? So optimal storage order for your data depends, for your algorithm, depends on the architecture, right? What we learned from that is that data layout mappings need to be configurable and an integral part of your API design. Another thing, memory traits. A lot of these hardware things have a lot of special access hardware. If you ever looked at the PTX description of CUDA, right, what it actually can do, how you can get to memory, right? I don't know how many there are, but there are definitely multiple dozens of ways of loading stuff from a memory location. There's atomic operations, there's in all kinds of flavors, right? Like with different access semantics and stuff like that, different memory orders. There's non-temporal reads, there's different flavors of that, like, oh, I'm caching it, but I'm marking it as evict first. I'm not caching it at all, and stuff like that. There's special purpose caches, right? You can use this LDG intrinsic to load through some texture cache thing or whatever, right? And so on and so on. Here's an example, GPU texture cache. It's essentially a cache which is basically there for read-only random access with a lot of locality, right? I'm trying to filter or run some filter over my pixels, right, and do some interpolation or whatever. Now, on the latest hardware, it doesn't actually matter much because they unified their L1 cache and their texture cache and stuff like that. But if you go like just a couple generations back, and you did that, if you didn't use the texture cache, for example, for molecular dynamics, right, you gave up 2x in performance, right? Just because you didn't use that special, funky, original for graphics intended access path. So what Kokkos View can do is, it actually has another template argument where you can set memory traits. And these memory traits are largely descriptive things of what you're doing. And we are trying then to map that to hardware capability, which might help that kind of scenario, right? So in this case, I have a const view of random X and will do random access. That's what the user told me. So I say, oh, you know what? There's a special access path for that on GPUs. I'm going to give you that. And if you don't use that, you miss out on a lot of performance. One of the things we learned there is also that you really want this stuff to be descriptive and not prescriptive. Because what this stuff is actually called on each individual hardware, right? What you could use for a specific kind of use case scenario, right? Depends very much on the hardware, right? And you don't want your user to need to know exactly, oh, what is texture cache and how does it behave and which situations should I use it, right? The user knows I'm going to do random access on const data, right? He doesn't know what texture cache is on a GPU. So, putting that all together, right? This is kind of the signature, not really, but almost, of Vue. The not really is that all these template parameters to the right, except for the first one, are actually an argument pack. But we enforce after the fact some kind of ordering there. Every argument is optional, but we enforce, if you give us multiple, we enforce a certain order. Essentially to decrease the number of combinations of types which are kind of the same type, right? Okay, so in Kokkos view, the data type is something like this. You get the value type, and then you get a combinations of stars and arrays, right? That doesn't actually say we store it that way, right? It's essentially just a type tag for us to deduce dimensionality. So a star means runtime dimensions, and a bracket with a number in it means compile time dimension. The reason that we didn't do just bracket without anything, bracket without anything, bracket with a 5 or whatever, is that it's not actually a legal C++ thing to write. So we couldn't do that. We could do this. Note that we do support compile and runtime dimensions mixed, which turns out to be really important. One reason is, it turns out in physics, right, we often have bracket 3 at the end, because it just so happens that reality is three-dimensional, largely, right? Then the next one is layout. The most important layouts we have is layout left, layout right, which is Fortran array style ordering, C style ordering. Why layout left, layout right? Because leftmost or rightmost index is the stride 1 index, and then you increase strides in the other direction. Layout stride, arbitrary strides in each dimension, and then we have things like tiled layouts, and users have done all kinds of other things. Then space is the memory location, and there you get things like host space, which is the native space of the process thread, right? So if you call new, right, or malloc, that's the thing you would get. And then there's more or less architecture-specific spaces, and I'm just mentioning a couple here. So CUDA space would be CUDA device accessible memory. Then CUDA UVM space is host device accessible memory, where the pages will migrate back and forth. And CUDA host pin space is memory which is accessible by both, but it's actually pinned on the host side, right? And each of these memories has different uses, right, for different people in different scenarios. You may want to use one or the other, right? And then we actually are introducing aliases to that so that you don't have to write CUDA space, hip space, SYCL space, and so on. And then the memory traits are these things which change access behavior. You can imagine things like restrict, aligned, atomic, all kinds of things. Okay. Let's look at the next problem. The next problem is hierarchical hardware. We have hierarchical hardware, and that's really problematic because if you look at this thing, right, this is this matrix add I just had. And I'm now keeping the product of n times m constant. So the total amount of work I'm doing is the same. I'm just changing how much work do I do on the outer loop versus the inner loop, okay? And what you see there is that I need on the order of 100,000 rows in order to get anywhere to peak performance on the GPU. Okay? Well, on the CPU, I start with 1,000 here. This thing only has 16, 32, 24 cores or something like that, right? As long as you're not below that, it doesn't matter, right? The parallel 4 gives you enough work per thread and you're done. But you need these 100,000 rows here to saturate the GPU bandwidth. Why is that? The reason is this kind of how this GPU is built, right? You have the HBM memory on there, and you have some L2 cache, and then you have these kind of things, these kind of blocks there, right? And each of these blocks has cores in it, which can do math. right? Each of these things has its own L1 cache, and scratch memory and whatnot, right? And might have registers. And there's a scheduler, and that scheduler is essentially taking chunked work and distributing it across all of these core regions, right? And says, oh, who has space to stick more work on it, right? The problem is we have a lot of these guys. So of these multiprocessors, these things which are kind of a collection of cores which share the same L1 cache. You have on the latest NVIDIA versus AMD things, you have 132 or 104 of these multiprocessors. And each of these has up to 64 or 32, depending on whether you're on AMD or NVIDIA, resident warps or wavefronts. This is essentially kind of a collection of threads which works in unison, like a vector thing. Each of which has 32 or 64 threads. And if you multiply all of that up, right, you end up with up to 270,000 resident threads, right? And on NVIDIA, this stuff is actually pretty close to a C++ std thread, right? You actually have forward progress guarantee and everything, right? And you have 270,000 of these guys, which is a lot of concurrency. So what you need to do is you need to expose hierarchies, right? You need to make possible to exploit that hierarchy in the hardware. Remember, I have these things, right? I have these 103 multi-cores, right? Which each can have like 2,000 threads on them, which share an L1 cache, right? I better expose that in my programming model if I have also hierarchical algorithms, right? Because I can make use of that, right? I can share the same cache, I can share scratch space and whatnot, right? And so in Kokkos, we do that through nested parallel loops. We use different policies there. In this case, you see I'm having this team policy out there, which essentially says, and I come to that in a little bit again, I want to iterate over these n iterations, but each of these iterations is going to get a whole group of threads to execute on, which then are available to do nested parallelism. Okay? But otherwise, I have two parallel loops, which again, both don't guarantee any ordering, any sequencing or whatnot, right? And if you do that, you see that now I can get that regime working much further to the left, right? I don't have that fall off, at 1,000 or 10,000 rows. I have a fall off on the other side because the work per team is starting to be really, really small, right? And setting up a team, as in particular in Kokkos, takes a little bit time. So if every thread then only does 2 memory loads or whatever, right? I have overhead I'm paying for. So the lesson learned here is that hardware is hierarchical and algorithms often don't expose enough parallelism on a single level. You need to support nested parallelism in order to make this kind of stuff work. Side note on that, and it would be really nice if that nested parallelism has the same semantics, right, as your normal top-level parallelism, right? Because it makes it easier to reason and compose code. So that gives us the policies and algorithms or patterns in Kokkos, right? So we have a set of fundamental algorithms we combine with execution policies, which essentially tell you, how do I assign threads to stuff, right? Or how much parallelism do I want on nested levels, more or less. So the parallel force here, the most important, policies or patterns are parallel for, which is essentially just, execute the callable and times or whatever, with no dependencies whatsoever in between them. Then there's parallel reduce. That essentially says every callable is producing an output variable, and I'm going to combine these output variables to produce one global result at the end. I do a sum reduction. There's a parallel scan, which is essentially you conduct a mathematical scan, right, of the output variables of every callable. It turns out if you do this concurrently, right, you actually need ways to execute the callable twice. So the callable actually knows whether it's in the first accumulation phase or the phase where it actually got the scan value. In serial, you can just go once through. Don't worry too much about it. And when you combine that with policies, right? Range policy, 1D index space, I'm just going from 0 to n or begin to end, using all the parallelism available. MD range policy, I have multidimensional range, also index space, right? I have a n by m by k space. Team policy is a 1D index space, but I'm assigning a team of threads to each iteration. And when the team thread range is kind of the corollary to the range policy, just that or maybe to the team policy, I have a 1D index space. I'm already inside the team policy, right? So I have a team handle already. And I still reserve vector level parallelism for third nesting level. It's the same. Let's just start this a bit. One thing which comes on top of that is with resource handles and asynchronicity. So I handed this team handle, right, to the nested thing. That was what I got from the team policy instead of just an index. And essentially the team handle is the handle to the group of threads, right, which can do certain things. But basically the resource handles is just the equivalent to like a handle to a thread pool, a handle to a CUDA stream, to a SYCL queue, to a CUDA block, to a CUDA warp, HIP, wavefront, whatever, right? It's an expression of who's gonna execute the next thing I'm gonna hand this to or use this with. In Kokkos, these things also contain references to things like scratch space for reductions and stuff like that, right? All the kind of data we need to do our algorithms. In Kokkos, most of our operations are asynchronous. So if you dispatch in CUDA, right, this multiple chevron thing, it actually is a one-way dispatcher, right? It goes to the GPU and your CPU thread is going on. And essentially what you need to do is you need to ask the GPU, please wait on my outstanding work, right? So that it's actually done. So that's what we do in Kokkos as well, right? So if you do a parallel 4, it just starts, it launches, and you have to explicitly wait for outstanding work to finish. What we do is we do that with these resource handles, right? So if you have a function and it gets like 2 resource handles, right, you can use them for 2 different operations. And what then happens is that these 2 parallel for loops might be executing at the same time, right? It might even be that one of them executes on the CPU and one of them executes on the GPU, right? Depending on what resource handles you got. And then you have to wait on these guys, for them to know that they're done. There is also dependency-based dispatch in Kokkos, but at this point, rarely any application uses that. Right? For most of them, it's fine to have essentially one queue you just dispatch work in, and you mostly just want to overlap, all the launch latencies, and then they are fine to wait. Right? There's relatively little in terms of task parallelism in a lot of the applications we have where we want to exploit that. Okay, with that, I'm coming to the 6 Kokkos abstractions which come from that. We have 3 for data structures and then 3 for parallel execution. And on the data structures, right, it's the memory spaces. We need a way of reasoning about where memory lives. On the execution side, we have a similar thing, execution spaces. We need to reason about where stuff executes. We need to reason about memory layouts, and we need to have execution patterns, right? You need to write your thing in a way which is kind of, the compiler or the runtime can reason about what you're trying to do, right? You have to express it in some well-defined patterns in order to make it mappable to all these architectures. And then we need memory traits to get all these, atomic and other kind of special access patterns. And we have these execution policies that I talked about, for like saying how much nesting do we actually want. If you put that all together, you end up with something like this, and I'll step through that in steps, right? So your functions get data structures which know about where the memory is. Your parallel 4 gets an execution policy, right? An execution space instance where the exec. And these 2 things know about each other, so you can ask, did the execution space, the resource handle you handed me, right? And the data you handled me, can that actually access these 3 things, right? Because otherwise I'm gonna throw an error on you. Instead of failing at runtime with a memory fault, right? We have execution patterns, parallel 4C in this case, which take execution policies and execution spaces to figure out, where to execute and how to execute there. And then we have a memory layout. In this case, I specified the memory layout explicitly for the 2D thing here, layout right. And the reason is that down there, that nace ij, right? I'm accessing that in a nested loop. So it's always going to be the rightmost index, right, which I want to be the fast index. So I know I want layout right here always, because that's the way I set this up. And then I have a memory trait here, right? I actually need to do atomic updates here, because otherwise I get race conditions. So I'm adding the memory trait atomic to the incoming output data, because I know that the way I wrote the algorithms, I'm getting race conditions otherwise, right? The caller of the function didn't need to know that. I'm adding that memory trait locally for the use case, for the way I wrote that algorithm. Okay, now, Jana actually said something this morning, be clever only when you need to be, right? And it turns out that many of the parameters you saw here are the same based on the architecture, right? So if you're compiling for a specific architecture, often people want all the same arguments, all the time for a lot of these things. So what we do is we actually default a lot of that. We have something called default execution space, which knows about its memory space, which knows about its preferred array layout, assuming you parallelize over the leftmost index. And so instead of writing that all out explicitly, you could just write that. That would actually give you the same type. This would give you the same, not the same type, but the same in practice, right, implementation. This would give you the same thing. And this would give you the same thing too, right? So people specify arguments when they need to, right? And otherwise just leave the default in. Same for execution. So in the simplest case, you give it an integer and a functor. But if you want to go further, right, you can tell it explicitly, I want a range policy. You can explicitly tell where to execute. You can control the index type used internally. You can set chunk sizes. You can tell it, oh, I actually want lower occupancy on my hardware because I want less contentions on the cache, right, and stuff like that. The lesson learned there was make simple things simple, right, and make the complex things easier to do. But the programming model is not enough. You also need things like tools. The common issue here is that abstraction layers obfuscate profiler output, right? If you run a normal profiler over Kokkos, right, it will tell you that all of your time is spent in some header file inside of Kokkos, because that's where we happen to write parallel 4, right? Or pragma OMP parallel 4, right, in the CPU backend. So what we did is we actually designed profiling into the API. One of the things you can do is you actually have to give Kokkos views names. When the view actually owns its allocation, you have to give it a name, which means that our profiling tools, when you have a, say, bounds check access error, right, can actually tell you the allocation you tried to access out of bounds has this name, right? The parallel 4s get names, which we can then provide to other things. In Kokkos, we have this runtime hook system, and it's always compiled in. Basically, what you can do is you can at runtime set an environment variable to point to a dynamic library. We will open that. We will see what implementations of the hooks you have, and we will hook them in, right? We fill these function pointers. And that allows us to provide that information, things like labels for parallel 4s, to tools like vTune, Nsight Systems, HPC Toolkit and whatnot. And what you see when it actually shows where, oh, you did a parallel 4 with an XB, right, which you gave the label XB, which is really, really useful for people, right? Build helpful debugging and profiling capabilities into. What? Oh, talk here? Yeah, okay. Kokkos support was really important. We have this huge lecture series, 15 hours of recordings of stepping through all the things we can do, covering all the kind of things you want in scientific computing. And we're using Slack as primary direct support, right? Kokkos kernels is the Marv library. One thing, if you're in scientific computing, you might be using BLAST, which has this nice C interface where something like a matrix multiply takes, 11 parameters or something like that. A lot of which are ints, which mean something. If you call Kokkos kernels, right, all these things like strides and dimensions are already encoded in the data type, in the view. It knows about its sizes, right? So you only pass that thing in. And it also makes it layout independent, right? Okay, with that, I'll come for a little bit to the building blocks in the future C++ standard. One of them is MDSpan. And I'm really proud that we made that. MDSpan also, looks kind of similar to Kokkos view, right? It has an element type, which in this case is just the value type. You have extends, layout, and accessor. So the element type is a fundamental scalar type. And the extends are the actual, runtime versus compile time extends. It's kind of like in span, right? You can use dynamic extend versus an actual number there. Just that it takes multiple. The std extends also encodes the index type you're going to use, right? You see that where the int, 5, std dynamic index, 4. That's a 5 by n by 4 array, 3D array, or extend object, using int as index types. The layouts are the same thing as in Kokkos, right? They're just these kind of, switch between the different things. They're actually called the same, layout left and layout right, and layout straight. An accessor is the customization point to do all the special stuff. It essentially holds what is the pointer type this MDSpan is using, and how do I get from this data handle plus an offset to a reference. So that's essentially kind of the equivalence to Kokkos view, right? There's an implementation here on GitHub.com Kokkos MDSpan. That's our reference implementation. So this is an accessor, right? As I said, it contains, what is the data handle type. Actually, I should have updated the slides because at the last minute we renamed pointer into data handle. So basically, pointer is something like the data handle. It doesn't need to be element type star. It can be, in the simplest cases, element type star. But we do even things like that is a window to an MP, an MPI window for communication across the system, right? Or something shitty like that. We also have then, the reference type, a thing which we return. And yeah. So how would you use that? One of the things you can use that for is memory space access, right? Basically, you say, I have now a thing which is specific to the CUDA space allocator, right? My accessor for that. And that accessor in its access operation will error out if you try to call that on the host. Boom, you have memory safety, right? Access safety. Atomic access. Basically, I'm just going to return an atomic ref to that thing instead of the thing itself, right? The value type. So I return the proxy reference as an atomic ref reference, which is in C++20. And I get atomic access on every access to my MDSpan. We can use that to make linear algebra better, right? I showed you that little example, right, with these 11 parameters for calling BLAS, right, which is kind of very shitty. If you look at the std_linalg proposal we have done, you now just take MDSpans as arguments. And so matrix product gets an execution policies and 3 matrices, and that's it, right? The matrices know about their strides, their layout, the dimensions and whatnot, right? You don't need to pass these in as parameters. The other parameters we actually also encode in the MDSpan. For example, if you want to call the C-BLAS overload where you scale one of the matrices as part of your operation, right? You don't really store it, right? So you don't overwrite the memory. You just do it during the computation online, right? We give you just a different accessor. So you call the scaled function on A, and what that returns is a new MDSpan with an accessor, which upon accessing a value will multiply it by 2, right? If you want to transpose it, it's switching the layout, right? You just you take the original layout and you switch the 2 indices, right? If you want to conjugate, you return a complex where you conjugated the complex on the fly. And that makes for a much cleaner interface, right? The implementation doesn't even need to know that you want to conjugate, right? It just implements one plain matrix multiply, and it will do the right thing automatically because it all happens implicitly in the access of the MDSpan. So where we want to go from there, so for the next things we really want is we want to combine these special accesses and layouts with access on layout aware BLAS. So one of the things we think we can do there is we could, for example, leverage fixed function units, right? If you, for example, know I'm getting compile time 4x4 matrices, right, with the correct layout, I actually know that I can map that, say, to a tensor core on the GPU, right? So it makes it much easier for people to express that in a portable way. And if you don't have a tensor core, right, it will just insert compile time optimized, code for 4x4 matrices multiplies, right? We are working on a standard set of accesses with descriptive properties, things like maybe that's something we want, right? Local random access, non-temporal, obviously the atomic, right? Aligned, all of these things, right? Are access. Everything you could put on a, in particular, every attribute you could put on a pointer, right? You probably want an accessor which expresses that, right? And we want to make that so that it enables vendors to map to special hardware, right? And everything. And then the question, can we make C++ memory space aware? There is no concept of inaccessible memory in the standard right now. It's not 100% clear that we fully need that, right? If you have HMM, it's a kind of a new thing in the Linux kernel, it actually turns out that you kind of can access most memory. It's just horribly, horribly slow if you happen to access the wrong memory, right? So you could imagine that in C++, what we do is we have allocators and accessors which go together and maybe things for execution policies, which just say, I'm affine to that memory, right? I can do that fast. I can ask my MD span, what execution policy should I use in order to get fast execution of my algorithm, right? Things like that would be possible even without changing the memory model itself. So in summary, I think productive performance portability is possible with the right semantics. I haven't shown any real performance data here, but it truly works, right? We have codes, some legacy codes we ported where even people who had already implemented raw CUDA and raw CPU. And in most of the big codes, it actually turned out that the Kokkos code at the end was faster than either one, largely because we constrained the user in not doing stupid things, right? Suddenly we weren't allowed to allocate memory anymore in the inner loops. And lo and behold, the code on the CPU ran faster. A lot of it can be integrated into a C++ standard, and we are working on it, right? We have std span, std proposals, parallelism. I think the biggest challenge, as said, is the memory model with the disjoint spaces and the multiple ISAR issue, right? I think we need to think more about integration of tool support into our public APIs. Stuff like being able to name objects, right, in your primary API without adding some extra, callback to a tool, right? I think is really, really powerful and useful for users. And we haven't done any of that in C++ standard at all. And one lesson learned over the last 10 years in this project is you need to be really careful about what you expose in your public interface. Because it turns out users will use every single mistake you did in exposing something you didn't meant to expose and will critically rely on it, and that you can't possibly ever change it again. So that's it. With that, I think we have a couple minutes left for questions.
Thank you so much. I have a question. That library, I never used it, but it looks like really complicated stuff. And my question is, have you ever thought about writing a new compiler for that, or some kind of domain-specific language?
So it is complicated, right? But it is pretty much, vanilla C++, abstractions, right? The benefit of doing it via an abstraction is that on every platform we buy, we use the compiler supported by the vendor, the primary optimized compiler by the vendor, right? And that is a really powerful sell for our users because they want to be able, when they get a compiler bug, right, or whatever, to go to the contract with the platform and say, fix this.
Okay.
Thanks for your talk. I really enjoyed it. A question about compression over the GPU bus. Is that something you guys are handling, or because that was big for the last 5 years ago at least? But.
We are not doing it. It turns out that in most of our scientific codes, we are so freaking latency sensitive. If you ever move data back to the CPU, you're kind of dead in the water anyway. We almost never do that in our real applications. We are almost always GPU resident. We have thought about it though, where we actually at some point started looking into doing this thing also via accessors, right? You could potentially do that. You have a host print allocation you can access on the other side, right? Yeah. And the accessor on the fly, right, will potentially unpack data and stuff like that.
Well, sorry, I don't want to monopolize, but you said you're having trouble accessing the memory. So how do you get to the data, like without transferring it back to the GPU? Like that wasn't clear to me. Maybe I'm just missing something.
No, we have performance problems, right?
Okay.
Not in theory we can do it, right? If we are really careful where we do it. It's just that it's, the boss is something like 10 to 20x slower than our GPU memory, right? So it's really costly, and the latency is super high.
Yeah. Okay, thanks.
Hey, this is not a question, but I really liked adding atomic to the memory space. That was cool.
Oh, you mean to the, you said
we
that,
took in memory space.
adding the atomic to our views, yeah.
Uh-huh. And I also have a question.
Yeah.
When you use transpose for the accessor, do you use that with Kokkos to alter the accessor that you use on the GPU? Or
no,
not?
we are not doing it in Kokkos right now. So in Kokkos, the Kokkos kernels interface actually still has the stupid kind of string transpose argument.
Okay.
So it does it actually does it internally, right? What we actually do is we internally take the data pointer out and we take it, instead of using, say you got a layout left, we now give you we give to the internal implementation a layout right of the same data.
That's what I was going to mention. I was worried it would mess up the layout left versus layout right configuration.
Yes and no, but it turns out that you can actually just look at the strides to figure out what vendor call you actually need to call, for example.
Okay.
So it's all, Oh, the question was about layouts and layout transpose, how that works. Okay. We are basically out of time. If there's more questions from people, right, I'm going to be here the whole week. I'm leaving on Friday. And we have a panel session, right? And you can ask me about all the nitty-gritty details I didn't tell you about here and all the other problems we might have. Thank you so much for your attention.